Today we are privileged to have the honor of having JunYi from A-Star. JunYi works with Leonid Krivitsky. I think you graduated recently from Princeton, if I'm not mistaken.
Yep.
Working on experimental stuff, spin mass stuff, spectrometer. I do not know the details. Yeah, but aside from that, of course, today you're going to present to us some recent work that you have done on deterministic, scalable, and efficient initialization of arbitrary quantum states. So I guess the floor is yours.
Okay.
And before that, maybe Leonid, you have something else to say?
Well, I just want to express my gratitude to CQT colleagues for this opportunity for us to present. We are really looking forward to your feedbacks. So please feel free to ask JunYi and pre-fill all the questions. And yeah, thank you very much.
Right. So floor strictly yours now.
Thanks, Craig. Yeah, so this is, I have to say, as Craig said, I worked on experimental atomic physics in my PhD, looking for axions, dark matter stuff. And so this is strictly speaking not my field, but I was called in to help lead this IBM challenge project after we got it. And so that's why I'm here. But I think we found some exciting results, and I want to be able to share them with you today. Okay, I see. All right. So initialization reminds me of when I first went to college. I had my first computational physics class. I was introduced to this term, garbage in, garbage out. My professor basically says that, well, computer is just a computer. What you get out is pretty much what you put in. If you put in garbage, you're going to get garbage out. And yes, the quality of information cannot be better than the quality of information that went in. And for a quantum computer, it's the same, and it's true. You can't get better information out than what you put in. So just to be clear, when we talk about initialization, classically on a classical computer where you have a register of bits, you basically initialize them either to 0, 1. In the quantum computer work with qubits, you have a register of qubits. You initialize, for example, one way to initialize them would be to initialize the states of the quantum vector, or the quantum state vector. So practically what this just means that, if you consider a quantum state expanded in its basis vectors, then A is basically the expansion coefficient, and you want to be able to determine those expansion coefficient when you initialize a quantum register. And the first thing I want to note is that this is actually kind of difficult, surprisingly. And so, for example, if you're in quantum finance, you want to have a normal distribution for your Monte Carlo. One way to do that is you sort of prepare your states as a superposition of states such that the probability is a normal distribution. So this is just the square root of your normal PDF up to some normalization constant. We're going to work with 5 qubits here because that's what we sort of publicly access on IBM's quantum computers. So you have 32 states. And X is just basically your standard computational basis state. Well, one way to initialize it is a standard routine that on Qiskit, which is used to program IBM's quantum computers. It's a deterministic routine. You put in the state, you put in the amplitude you want to initialize to, and it basically comes up with a sequence of gate operations to do the initialization. As you can see, these are experimental results from running it on IBM's quantum computer. The error bars just are the expected statistical spread just based on the probability, the expected probability, and the number of shots that we put in. So they're just there really just to tell you that we ran it for enough shots so that statistically it's not an issue here. But in any case, you can see that clearly this looks nothing like a normal distribution. Now, if, however, you say, well, maybe I don't want to initialize it exactly, I'm happy with an approximate initialization. And I want to say, for example, initialize it to a state like this, given by the yellow dots. And then if you use our routine, you can, there's a standard way to find these kind of states that are optimally approximate with lower entanglement. And the key thing is that they have lower entanglement. And so we are able to initialize them much better. And you ironically actually get better fidelity when you try to do this approximate initialization rather than trying to do an exact initialization. So just for, I think most people here know, but for people who are maybe not completely familiar with it, the main reason why this is so difficult, might be surprising, is that due to hardware limitations, just certain amount of operations that you can perform on each qubit, and these are just gate operations, and on each machine there are a set of native gates, and each gate basically introduces additional noise, and what's typically most problematic are your multi-qubit gates. So in this case, your CNOT gates, the 2-qubit gates, it's just hard to implement them with high fidelity, and it gets worse if you operate, for example, if you want to operate a 2-qubit operation on non-neighboring qubits, so for example Q0 and Q3, because on our actual hardware there's limited connectivity for the qubits, and so Q0 and Q3 can't talk directly, and so to implement that you need additional swap operations, which basically consists of more CNOT gates. So you want to, as much as you can, just operate on neighboring qubits. And roughly speaking, the amount of noise that you introduce is proportional to the depth and length of the circuit, as well as the number of gates that you have. The first thing to note is, okay, so let's say we saw that the standard method, the analytical isometric decomposition, it's noisy, but are there other ways to do it? And this is a problem that other people have tried to solve, because obviously if you can't initialize a quantum computer, it's a roadblock to try to do a lot of other things, right? You can't get the first step done and done well, garbage in, garbage out. And the first thing to note is that initialization unitary is not unique. And what I mean by that is, let's say you start in your 0 state initially, and you want to initialize it so that it points like that, right? And there are many ways you can accomplish this. For example, you can take the most straightforward path down the block sphere. You can go for a little bit of a curve, or you can even try to do something like wildly crazy, but it still gets you back to the endpoint, right? So point here is that the initialization unitary is not unique. You can use many ones. And so some people say, well, okay, well, if the unitary U that this isometric decomposition gives us is not good, in the sense that it gives us a lot of CNOT gates, the depth of the circuit is very long. Well, can we try to numerically find a U that has less gates, shorter, shallower depth, compared to standard methods like isometric decomposition? And so one way that's quite popular nowadays is to use these variational circuits. And the idea basically is you just come up with some ansatz, circuit ansatz. It's somewhat arbitrary how you structure the circuit. You need some entangling gates, you need some rotation gates. But the main idea is that these gates are parametrized, they're variable. So the angles by which you rotate your qubit states are variable. And you basically optimize, well, you tune your thetas to optimize the loss function. And you keep doing that and hope that eventually you converge to having the output state that you want. One variation of a variational approach, pun intended, is these things called generative adversarial networks, qGAN, quantum generative adversarial networks. And the idea is basically people treat the circuit as a generative neural network. Your thetas are your weights, but same idea. You run it, you get the output. The main difference is that you feed it into a discriminative neural network before you get a loss function, you propagate it back. But it's the same idea. So you try to optimize your thetas to get a target state that is good. That's close to what you want, essentially. Now, we tried these approaches initially, and Preeti really did a lot of legwork exploring these approaches. But what we found is there are many issues with this variational approach that makes them less than ideal. So first of all, there's not really a general guiding principle for how you should select your circuit on how you should arrange your circuit. There's no guarantee, as far as I know, that a particular circuit topology actually will contain a desired solution, right? There we go. The loss function's gradient exponentially vanish for as a system scales. This is known in literature as a Baron-Plateau problem. The loss functions landscape, and this is what we found from our own numerical experiments, and I think I've seen some other papers that also report the same now, that you have a ton of local minimas all over the place. So it's hard to find the global minimum. Of course, the time required for this classical optimization step, I forgot to add here, this whole optimization is done classically because it's very hard for the quantum computers today to do it. But this time that you spend optimizing can negate any speed advantage of your algorithm. And lastly, the quantum circuit is a bit of a black box with very little physical intuition. And so we tried, like I said, this for a while, and I felt like it's not really working, doesn't generalize very well. And so I decided to just take a step back and just look at a problem with more like physical insights. I want to just list a few here that we will go on to show that we can actually achieve. So first thing to note, I think, is just that not every state is equally hard to initialize, right? Some states are obviously easier. So if you have a product state that's separable, you just need one layer of single qubit gates. And so you want a routine that is able to take advantage of these facts, that some states are easier than others to initialize. And intuitively, basically, states with less entanglement are easier to initialize, require less entangling gates than states with more entanglement. So we want a routine that takes advantage of this. Let's see. If so, if a routine like this exists, we also want to find optimally approximate states with less entanglement, which are then easier to repair. Intuitively, you only need multi-qubit gates when there's entanglement. Can we establish a connection between the two? Limited, as I said just now, qubit connectivity means that we want to use nearest neighbor gates whenever possible. And of course, generally speaking, we want to generalize an arbitrary state. Each qubit needs to be operated on by at least one gate. All right, now I want to focus on point number 2 first, and then later on we'll see how the rest sort of are achieved with our method. And to do that, we need to discuss this thing called matrix product states, which really is just a clever way of writing a wave function or a state vector. So, as I said, you can write a state vector in this way. These are basis vectors, and this is just a q-dimensional tensor that are the expansion coefficients. And what the matrix product state does is essentially rewriting this q-dimensional tensor into q 3-dimensional tensors. Each one of these tensors, in the literature, some people call them cores, MPS cores. It consists of 2 bond indices. I can think of these as summation indices and 1 physical index. So basically the quantum number in your state. By definition, dimension of alpha 0 and alpha q are 1. So, I wrote alpha 0 to alpha q sum here, but really you don't need to sum these, but it's just somewhat more symmetrical to write it this way. As I will show later, any arbitrary state can be written in a matrix product form, as long as dimensions of alpha are allowed to be free reign. And as we'll also see, dimensions of alpha n is a measure of entanglement between the nth qubit and the subsystem jn plus 1 to jq. Now, and just as a quick consequence of that, you realize that if dimension alpha n is 1 for all n, this just immediately reduces into a separable state. So you can just, you don't have to sum over the alphas, and you just break up your sum over j's. And so you see the MPS has some very nice intuitive features that sort of has a bit of locality in the sense that it parses out the j's, and the alphas give you some information about the entanglement between one qubit and another, and the rest of the bipartition. So you can do this MPS decomposition from a q-dimensional A tensor into Q cores. You can do it analytically for a few special cases, but the nice thing is it can always be done numerically via a series of reshaping and singular value decomposition operations. So for example, if you start off this q-dimensional tensor, I'm going to use this notation where if I use a semicolon, I'm viewing this as a matrix. So everything on the left of the semicolon is the rows, and everything on the right of the semicolon are the columns. So you should think of this as q minus 2 to the q minus 1 dimensional columns. Sorry. All right. So viewing A now as a matrix can perform an SVD, and so alpha 1 dimension of alpha 1 now is the rank of this A as a matrix. And normally there's 3 matrix, of course. When you do an SVD, I've combined the second and the third one into this B matrix. And then you do a reshaping of U. So this gives us our first core. I remember that alpha 0 is dimension 1, so it costs you nothing. And then you reshape B as well so that J2 becomes on the row, and then your column starts from J3 onwards. And next, you do another SVD on B, and you get U and B. You reshape U to become your second core, and you do an SVD on the B as well. So it goes on and on until you basically completely decompose it into MPS form. And the point here is that any state can be written as an MPS. Now, there's of course a very close connection. They're basically more or less the same thing, SVD and Schmidt decompositions, and we see that dimension of alpha n is basically the Schmidt number between qubit n and the subsystem Jn plus 1 to Jq. And the point here is that dimension of alpha n is a measure of the entanglement between qubit n and the subsystem Jn plus 1 to Jq. Now, this is nice because writing this this SVD formalism sort of allows us to find these very systematic way of finding this optimally approximate states with lower entanglement. So if this is the SVD of A, then by Eckert-Young's theorem, it tells us that the best RK rank approximation of this matrix A is basically given by AK, where you basically keep the first RK singular values, keep the first RK largest singular values. And in fact, this is optimal in both the spectral as well as the Frobenius norm. And the error in the Frobenius norm is just the quadrature sum of the singular values that were truncated. So RK plus 1 to dimension of alpha. What this means is that you can get locally optimal approximate states with lower entanglement simply by truncating the bond dimensions. I say it's locally because as you recall from the previous slide, when we decompose it into an MPS course, it's sequential. And so at each stage, Eckert-Young basically guarantees that it's locally optimal. But of course, because it's sequential, you might not be globally optimal. But this is actually a known problem, and people in the tensor network community do use variational truncation to find these globally optimal approximate states, because people use these for image compression and stuff like that in the computational literature. All right, so just to sort of see this in action for a bit, let's say you have, again, coming back to the normal distribution that we saw before. If you decompose it in the way that I've just described, you get these singular values from each of the bonds. And this is the exact case. If I truncate it by choosing 1, 1, 2, 2, for example, this is how you get that approximate state with lower entanglement. All right, now. Another thing to note about MPS is that this decomposition is not unique, since each core can change in such a way such that when you contract all of their bond indices, it doesn't change A at the end. So this is sort of some kind of a gauge freedom, if you will. And you can use this gauge freedom basically to transform any normalized MPS into, say, what people sometimes call a right canonical form that obeys this orthonormal relations. Now, the key thing I want to point out is that you can interpret these orthonormal relations as saying that each MPS core has dimension alpha n minus 1, these number of orthonormal complex vectors, and they are complex vectors that are dimension of 2 times dimension alpha n. So yeah, that's basically what is, once you put it in this form, you can interpret each MPS cores as having this amount of orthonormal vectors in the complex vector space. All right, so that tells us about matrix product states, but of course, we can apply that to our target state, but we haven't really done any work in trying to initialize that state. We know we can write any state in that form. Now can we use that to help us initialize it? And so we're gonna write down a circuit ansatz with just 2 very general requirements that I sort of talked a little bit just now when I discussed about the physical insights. One, each qubit must have at least 1 gate that operates on it. And 2, each nth gate is a dn qubit nearest neighbor gate, where dn is a variable that depends on the entanglement. And so you can write down, you can draw the ansatz and it looks something like this. And D1 here, like I said, is variable. It can change depending on the entanglement. And because it can change, it has to be sort of this form so that each gate has at least, each qubit has at least 1 gate that operates on it. Now, note that if dn is 1 for all n, then this circuit very nicely reduces to a single layer of single qubit gates. And also just by construction, the ansatz scales linearly with the number of qubits. All right, so given this form of the circuit, we can sort of write down the unitary matrix that this circuit gives you. You can write it down something like this. One thing to note is, so using this notation, a set of B1 basically is a set of all B indices that have a subscript of 1. But physically what it means is, you're operating from J1 prime to JD1 prime, for example, for your first gate. J1 is no longer operated on, so that's your final state. But then in principle, the rest of them are going to be input states to another gate. And so we call those input states to another gate, like we label them by B. The superscript basically tells you which gate they belong to or their output from. And so, when you try to form this unitary matrix, you basically have to sum over all of these B intermediate states, B1 all the way to BQ minus 1. Now, let your state vector, this is our target state that we want to initialize, and it's written in an MPS form. Now, what we want to enforce is that you want to find a U so that when it operates on 0, you get our target state psi. And that means we want to see that when you sum over all of the sets of B here for your G, you basically get A when Jm prime is equal to 0 for all n, right? So this is we just start from 0. And now, note that there are Q physical or free indices on both sides of this equation, and there are Q minus 1 summation indices. We sort of view this as one summation indices. There's Q minus 1 of them on both the left and on the right. And this suggests a mapping between AN and GN, and between alpha n and the set of Bn, essentially. And to do this, you need to first ensure that dimension of this, the dimension that is spanned by these B's are greater than or equal to alpha n. And so you can enforce this simply by choosing the dn to be 1 plus log 2 well, the roundup of log 2 dimension of alpha n. So if you choose dn in that way, then basically this is always ensured. And also note now that if you make this choice, that for a product state where basically dimension of alpha n is equals to 1 for all n, then dn is equals to basically 1 for all n. And this is nice because what it means is that our circuit essentially by construction reduces to a single layer of 1 qubit gate if the target state is separable, which is exactly what we want. And then what remains is how to do this mapping. This is unfortunately a little hard to see, but one way to see it is basically that each G has this form where it has basically sets of B, J prime, which are your initial states, as your columns, and as your rows, you have Jn and a set of Bn. And each MPS core has dimension of alpha n minus 1 orthonormal complex vectors. And so essentially what it comes down to, if you work it out in careful detail, is that you basically fill the first dimensional alpha n minus 1 columns of G, that's a unitary matrix, with the dimension alpha n minus 1 orthonormal complex vectors of an. Now, this is necessarily smaller than the number of rows in G, smaller than or equal to by construction. And so, if it's smaller, you just zero pad. If it's exactly the same size, you just fill it. And you will fill a dimension alpha n minus 1 columns. And once you have filled it, then you basically fill the remaining columns by requiring that G is unitary. So you have dimension alpha n minus 1 orthonormal vectors. You just find the remaining orthonormal vectors that you need to make G unitary. And so that really is the gist of the method. And so now in the remaining time, I'm just going to briefly, show more detailed results that we have from running it on IBM's quantum computers. So this is a normal distribution that you have already seen. This is isometry results. It has 59 C0 gates, 51 RZ gates, 39 SX gates with a depth of 109, fidelity of 0.788. If you use an approximate state given by this and you run it, we have 5 C0 gates, 35 RZ gates, 30 SX gates, 44 depth. So about an order of magnitude less C0 gates, half the depth, and a fidelity of 0.976. So we can get higher fidelity even though we are initializing to an approximate state instead of the exact state. Let's see. We can try this with a log normal distribution, again, of interest to the quantum finance community. So that's the exact state. You can try to do an isometry decomposition. You get a fidelity of 0.75. You can do an approximate state. In this case, it approximated pretty well. And then you run it through our routine. Again, you get about half the depth. I guess in this case, it's maybe 5 times less C0, but higher fidelity certainly compared to isometry decomposition. You can do it for a Sine distribution as well. And in this case, it's the normal one. The fidelity is 0.92, but we can do quite a bit better. So 0.995. About 10 times less C0 gates, almost 3 times shorter circuit depth. And the last one is just sort of a toy thing, which is that, a lot of times, especially when you scale up the number of qubits, a lot of times you're just hoping that your vector or what you're trying to initialize is sparse. And so you just sort of, at least in this case, I just assume a sparsity of 0.9, and I just randomly chose some basis states, a random distribution, and try to see if we can initialize them, how we do on these. And for this case, I have to say, physically, right, the reason the biggest advantage you get is when you have a state that is close to it, that has less entanglement. That's when this really shines. And so because this is completely random, there are some cases that are not so good and some cases where it performs better. This is one of the ones that it performs better. But anyway, so for isometry, you get 0.48. We do an approximate of this state. You might not be able to tell, but there's a little bit of a bump here as well. So the MPS basically ignores that bump here. It becomes like a flat line. And in this case, we can get, 0.911. So not too terrible, not too shabby. All right, so that's really all there is. And so I just want to conclude and say that we have demonstrated deterministic, and I mean deterministic, in contrast to a variational approach where you have, or you don't know if the solution, if the circuit that you have gives you the solution that you want. So in that sense, it's not deterministic. You have to go through the optimization routine and try to see. So it's deterministic in the sense that you give me the state vector, I plug it into my algorithm, it gives you the answer almost immediately. It's physically intuitive, and what it does is that you can initialize arbitrary states. In this case, we didn't really explore that too much because, like I said, the real utility of this, especially in this era, is being able to initialize those approximate states. But in theory, it works on arbitrary states. Uses nearest neighbor gates. It only uses multi-qubit gates when entanglement of the state requires it. It simplifies if entanglement of the state allows for it. It allows optimally approximate states of less entanglement to be found and initialized. And of course, tests on actual hardware shows that it works quite well. It gives you higher fidelity than trying to use an exact initialization. Sometimes you can get more than an order of magnitude less entangling gates and significantly shorter than standard isometry decomposition. And so with that, I thank you for your attention. This is Preethi. He did a lot of the variational approach work, numerical experiments. It's obviously me. And I just want to say we are shamelessly advertised that we are hiring for a new atomic magnetometry quantum sensing project. If you know someone who's interested in it, please direct them to our website, contact us. Yeah, so with that, thank you, and I'm happy to take any questions you might have.
Right, thank you, JunYi. Any questions from the floor? Let me see. Not yet. So you implement all this on Qiskit, on IBM computers, which means that you have, how does it compare with the standard one that they already have on Qiskit 2 by AER simulation?
So yeah, so for example, in this case, the standard Qiskit one will be these red ones. And then ours is the green one. Yeah.
See. And what is the, have you done it with other platforms aside from IBM?
No, we've only done it with IBM so far, yeah. But I think I heard recently that Qiskit now works on IonQ as well. So that,
yes. Yeah. So, yeah. So there are other platforms that one can try out to do a comparison.
Yeah, that's right. That's right.
Any questions from the floor? You can just unmute yourself and ask the question if you like to.
Hi, short question. So if I stand correctly, your method is based on MPS, right?
Yep, that's correct.
MPS is only, but MPS is like restriction, right? MPS is good at one-dimensional ground state of one-dimensional quantum systems. So if you want to generate a generic state, MPS wouldn't be an efficient way, right? Is that correct?
Well, not really, right? Because I mean, at least when we're thinking about this, are you saying if you, let's say, for example, if you have, I guess what I'm saying is,
let's say I want to do a hard random state, like would this method work well compared to the alternative method?
You can initialize. So wait, when you say, hang on, let me see if I can move to your slide that maybe makes it a little clearer. So you can expand any state into, you can expand any state as just in terms of its basis vectors, right? And it's one-dimensional in that way. I think, you know, this is quite general. You can write any state in this form.
But it's not efficient, right? The one dimension will increase exponentially if you have like a highly entangled state, which is not a one-dimensional, the ground state of a one-dimensional Hamiltonian.
I mean,
let's say a hard random state, the one dimension of each matrix will become very large.
Yes, it will be. I mean, so basically, if you have a highly entangled state, basically what this means is the alpha, your dimension of your alpha, you know, becomes very large. I think that's what you're saying.
Right.
But yeah, so in that case, all I would say is that you're going to have a difficult problem either way, because you can't run away from the fact that when you have a very high entanglement state, that essentially you're going to need a lot of entanglement gates. And so, yeah, you probably won't get that much of an advantage in that case.
But hard random states can be efficiently generated by hardware efficient circuits. So if you just take a row of, let's say, single qubit rotation and C0 gains and just repeat this layer a few times, I will get a state which is hard random. I mean, approximately hard random.
Yeah, I think, I guess
so
what I was...
it's the resource in that sense is not efficient. Of course, you don't know which state you're generating, but it's a state which is approximately hard random and has lots of entanglement.
Right.
So I'm wondering how this compares to your method.
So I would say the difference is that in that case, so that's basically when you use like a hardware efficient ansatz, right? It's a variational approach, right? And so I think that's the main difference. Like you actually have to go do the messy work of having to deal with not knowing whether or not this ansatz will give you what you want. You have to deal with the barren plateau problem. You have to deal with tons of local minimas. You might not find a global minimum, stuff like that. So your standard problems with a variational approach.
Okay. Okay, thank you.
Right. Any other questions from the floor? JunYi, you have a question?
No, I don't have a question.
No?
Thank you.
It's a random on the floor. So, right. If there are no other questions, perhaps then we can end this session. And thank JunYi for his wonderful talk, crisp and concise. Thank you very much for sharing.
Thanks.
Thanks.
Thank you.
Yeah, thank you.
Thank you, guys. Thanks.